plugs into this. So that's okay. So not only can we use Terraform to provision cloud-based resources like, say, virtual machines in GCP or GCS storage buckets or S3 buckets in AWS. But through this plugin model, you can use it for almost anything. And people create these providers, and they use sort of the model of Terraform to create almost anything. So in Kubernetes, for instance, you can create Kubernetes type elements. So it's not just for cloud resources. So let's see, back to PowerPoint here. Now the Terraform language has this notion of resources, which are cloud specific or provider specific. So here's an example showing a little bit of Terraform code that could create a compute instance, which is a virtual machine in GCP. And you can specify things like, like what kind of machine type it is, where it's going to be regionally, where it's going to be located, things like what kind of operating system you want it to be provisioned with. And the Terraform website is really good at this. So, but these resources, are cloud specific. So it's not like it creates an abstraction for you, like where you can just create a compute instance and then flip a switch and it turns it, from a Google compute instance to an AWS compute instance. These resources are specific, so your programs are sort of cloud specific. All right, so now the Terraform documentation is quite good, I would say. And just as an example, I often find myself just Googling for things like, let's say I wanted to create a GCS bucket. I might just Google for something like, and I use Terraform as I think Google's pretty good about understanding when I say TF. Yep, so the first hit that came up is this Google Storage Bucket resource. So in that slide, we were looking at how to create a VM in Google. Here's like the documentation for creating a storage bucket. So that's kind of the basic like overview or of like what Terraform is. So let's move on to a little bit deeper about how we write programs in Terraform. So there's this notion of variables. So you see them used here like var.machine type. So it's kind of like a parameter. So we're parameterizing our code. We don't want to hard code the machine type because that will only get us so far. So you'll see uses of different variables. And you have to sort of like declare the variable, and then you can see that the variable is used a little bit later here. So moving on a little bit. When you kind of create when you're coding stuff in Terraform, there's sort of different levels that you would work on. One is a project, which is sort of like this highest level of construct. And then a little bit lower, you can create these modules, which are sort of reusable components in Terraform. And so in our case, we have what GCP has this construct of projects, and it's sort of like this boundary of resources. And when we talk about multi-tenancy, there's a strategy where you can create or support multiple tenants in a single GCP project. And there's trade-offs to this, but sometimes depending on the way that there's some organizational aspects to this, but in some cases, like let's say creating a new project in GCP, maybe it would take several weeks to provision a GCP project. And let's say you have like dozens of tenancies, or when I say a tenancy, I mean sort of a group within your organization that is looking to construct resources on the cloud and then use those resources for things like analytics type of workloads. So the strategy, one strategy that we took was to minimize the number of Google Cloud projects that we create and house and allow to have multiple of these tenancies in a single project. So in order to do that, for a tenancy, we needed to create sort of boundaries around these tenants such that they don't interfere with each other in the course of their work. So there's this this notion, sometimes often referred to as this noisy neighbor problem. So you want to share a particular resource, but keep them out of each other's way so that they don't accidentally, or in worst case, deliberately interfere with each other. So think about even I don't know, processes on an operating system. Sometimes it's a similar analogy there. So what we ended up doing was using this Terraform module construct to create a module that represents a tenant. And a tenant in our current model, a tenant consists of a series of IAM constructs. And when I say IAM, it's like identity and access model. So a tenant would have a series of you can think of them as privileges and a series of resources. Some of them were sort of like foundational resources, like we figured every tenant might need a handful of GCS buckets, and every tenant might need a say maybe a BigQuery data set, and every tenant might need I think that's probably that's probably it. So a tenant would be composed of a series of IAM constructs, a series of storage constructs, and this sort of relationship between the privileges and the resources, such that the tenant would be the only entity to have access to their own resources, and that's part of that noisy neighbor, solving that noisy neighbor problem. So we would create and here's a kind of an example of it, where you can use this Terraform module construct to create this abstraction for a tenant. And within that, and then we could reuse this tenant module under the hood. If you looked at the implementation of the tenant module, you would see a series of IAM resources and maybe like a series of storage resources. So as an example, getting back to say the Terraform documentation here, like if I look for IAM, we should see an example of some of these IAM resources. Let's see. Well, and actually, like IAM sort of like is a cross-cutting concern. So you'll see things like IAM referenced within Cloud Functions, but there's also sort of core IAM essentials like maybe a service account. I guess the actually like going after these things via Google is a lot more efficient than going after them like within the Terraform documentation itself. So if I did something like GCP service account TF, even with a misspelling here. Yeah, so here's kind of an IAM construct, Google Service Account. So if you looked into the guts of the implementation of the tenant module, you would see references to these service accounts. And so for every tenant, we might have a handful of service accounts as well. So moving on a little bit. So there's this notion of Terraform state, which is pretty important. Like as you construct these resources, these cloud-based resources, Terraform is holding on to this state, which represents those resources. And if it was just one individual on a laptop responsible, say it was a very small organization and there was like one guy that was responsible for provisioning cloud resources, by default, when you execute Terraform operations, it would default to local state. So it would like kind of create just a local file on the laptop of the guy executing the Terraform. And that would be, it's actually like, it's not really good long-term, but it would work for this guy because next time he came to his laptop and tried to execute something, like the state would be in that folder that he executed the thing in, and Terraform would work as expected. But if his laptop got run over, that would be a problematic. Or in a more typical situation, you have in an organization, you have like multiple people, groups of people that are responsible for provisioning infrastructure and running Terraform code. And typically you also wouldn't be. So Terraform has this notion of plan and apply, and it's these phases of the way it goes through things. And so like for your first step would be a Terraform plan, where you ask Terraform, hey, based on this code and this state, if I asked you to run this, what is it that you would do? And it might tell you, well, I'm gonna change the machine type of this virtual machine from having 2 CPUs to having 4 CPUs. And then the individual in charge of running that code might look at that and say, yeah, that's what I want to do. So let's go ahead. And then they would say, then they would execute a Terraform apply of the previous plan. On the other hand, maybe there's a bug in that Terraform, and it might come back and say, well, I plan to delete 500 virtual machines in your production infrastructure. So in that case, if that's not what the guy wanted to do, they should be like, oh boy, let me kind of not apply that because that could be catastrophic. So normally we use shared state. So that's a strategy where Terraform allows you to keep state in a backend data source that's visible across multiple individuals. And typically individuals like humans should only do Terraform plan to kind of like check what their Terraform is going to do. And Terraform apply should be done by like a deployment system like a Jenkins. So that's what we do. And we use for Terraform state, we use like in GCP, it supports keeping Terraform state in a GCS bucket. In AWS, you can keep it in an S3 bucket, and there's various like Terraform refers to it as backend, and there's various sort of backend implementation that Terraform supports for holding on to backend state. So that's a little bit about Terraform state, very important. So the wrapper script. So when you execute Terraform, you have to kind of tell it where to find the backend state. And like for our sort of DevOps staff, people that are responsible for provisioning cloud-based infrastructure, it would be kind of cumbersome for them to type Terraform plan dash backend state equals the location of the GCS bucket for the environment that I'm deploying to, or something like that. So we have like a pretty useful, I would say it's like kind of like, almost required wrapper script that we use to run Terraform operations, and it has built-in support. It sort of has built-in support for specifying where the backend state is for a particular environment. So let's And so the way that this wrapper script works is you would kind of feed it an environment. And we have this notion, say, for instance, it's typical to have dev, test, and prod environments. So the way it would typically work is you Terraform operates like in sort of on Terraform files that it finds in your current folder. So it's like a command line style tool. So typically what you would do is set your current directory to a particular Terraform project directory, and you might execute something like Terraform plan or execute this wrapper that calls Terraform, and you might say something like Terraform or Terraform wrapper plan dev. So that would sort of point it at the dev environment, and it would execute plan, and it would sort of point it at where the right backend state is for development for that project. And yeah, and there's a few other things that it does, like it gathers. We also have standardized say cloud regions that we deploy to and things like that. So this is very helpful. So that's a little bit about the wrapper script that we use. Tenants. So I kind of touched on this before, that this notion of tenant is a combination of IAM service accounts, policies, which are sort of other kinds of IAM constructs, and they might say that this service account has the privilege or ability to interact with this particular bucket or something like that. And so we will spin up a few service accounts, like one to be used at runtime, and possibly one to use in the context of CI/CD for deployment. There's also the notion of a human interacting with cloud resources. And so like a human is also a kind of a principal. And there's this notion of groups like that can be backed by different groups. Like, so for instance, what we do is we use Azure AD groups and we associate humans with Azure AD groups, and we associate Azure AD groups with groups of policies in GCP, so that for a human executing something, they sort of like GCP like has a way of taking their credentials, understanding what groups they're in, and providing access to those policies, or applying the policies to the human that's executing the command. So this is also in play under the hood in Terraform, because Terraform under the hood is executing Google Cloud commands, and the Google Cloud commands are paying attention to the policies of the human or principal that's executing it. So typically we would execute these constructs as like a deployment service account for a particular tenant. And there's this notion of like an administrative tenant, like a high-powered tenant, or more of our sort of like the tenants which represent development groups in our organization. So like we're in sort of a DevOps group, and so like when we execute Terraform, we're sort of running under a more high-powered, a high privileged principal than when, say, one of our development groups is executing maybe a cloud function in GCP. They're executing as a service account that's associated with their tenant, which would limit the privileges of that cloud function to only get to the resources that tenant is supposed to gain access to. So a lot of sort of bread and butter security stuff going on here. So that's this abstract notion of a tenant and how it maps onto Google resources, and sort of implied is how we use Terraform to help construct those elements which compose a tenant. So, I would say generally that when you're sort of like constructing or provisioning resources in a cloud provider, and resources are not only things like storage buckets, but it's also these IAM entities, that doing it with infrastructure's code is kind of almost mandatory. Like, you could technically have a human go to the GCP console and construct service accounts and construct buckets and policies and grant access for this service account to this storage bucket. But almost immediately you'd find that it's like unsustainable to attempt to do it with a human. So you really need software to represent what you're trying to do in the environment. And really sort of reusable. That's, in that software, you really need reusable constructs like tenants. And this is where Terraform sort of like excels in that space. It's sort of like one of the leaders in those fields. So there's a few other players, but like Terraform is pretty big. GCP sort of like embraces Terraform, and if you look at the GCP documentation, they'll have often Terraform code snippets which show how to provision their various resources. And it would be sort of like roughly analogous to AWS has this stuff called CloudFormation, which is like a proprietary way through infrastructure's code to provision AWS resources. But Terraform is more sort of like cloud agnostic from a third party. It's open source. We use the open source version of Terraform. There is a product called Terraform Enterprise, which you can pay HashiCorp for, which adds a number of different enterprise features. So moving on a little bit, CI/CD. I touched a little bit on Terraform Plan versus Terraform Apply. So it's a little bit interesting from a CI/CD perspective because you kind of see, this isn't necessarily, I guess, like when you deploy new code to production, there's always sort of like the chance that you deploy something you didn't want to. There's a bug in that code, which is going to cause a varying degree of like problem, right? Like, so from the simplest bug to I misspelled a word on a website, to like like a kind of a really bad bug that like adds a 0 to when I move money around or something like that. Like, bugs in Terraform code can be catastrophic, because worst case is they start deleting resources that you provision in the cloud, very like potentially very important resources like databases and cloud buckets and virtual machines and Kubernetes clusters, and like really bad things can happen. So when it comes to CI/CD and Terraform, like it's kind of like important to have a human look at the output from a Terraform plan and sort of validate it and sort of confirm that, yes, I want to actually apply this operation. So we happen to use Jenkins, and through our we have Jenkins run this, both the plan and the apply. And so like we have a way for a human like in the Jenkins, looking at Jenkins to be able to eyeball the result of a Terraform plan and decide whether they want to apply that or not. It also, in general, CI/CD and good practices using something like Jenkins or an automated CI/CD system ensures that all the code that's being executed is in source code control, because Jenkins just gets its code from source code control, like GitHub. And if we did things like Terraform Apply from the desktop, it's possible that the code that we're executing on is only on the developer's desktop. They didn't check it back into source code control. They didn't have it reviewed. And so that's kind of like why we want something like a Jenkins to be executing the Terraform apply. Let's see. We yeah, and we have like kind of a generic flow in Jenkins that executes on Terraform. And we have sort of other forms of automation which allows developers to create repositories in GitHub and automatically create Jenkins jobs, which executes those Terraform projects. There's some interesting things that crop up in terms of Terraform and CI/CD and self-service, and like what it exposing Terraform to our constituents to the extent where it's not always safe, basically, to allow anyone to execute any Terraform. So a lot of times we've applied some other constructs to Terraform in terms of CI/CD, which either the Terraform that's executed is stuff that the DevOps staff has written and we execute it ourselves, or if we're exposing it for self-service, we do it in a way that just allows our development tenants to parameterize the Terraform, but not provide raw Terraform code, because there are other kinds of bad things could happen in that regard as well. So a little bit about CI/CD and Terraform in a shared environment. Terraform project patterns. So this is kind of touching on ways to expose Terraform to different kinds of constituents. So this is kind of touching on this slide here is touching on what I was just talking about. So there's this scenario where we as a DevOps group has a Terraform project that is used to roll out stuff for our entire community of tenants in one run. So for instance, we have like probably around 100 tenants now that we support within our organization. And we have one like consolidated Terraform project that lays out the IAM permissions for those tenants. So like there might be a situation where we're rolling out a new resource in GCP, like say, I don't know, Vertex AI, and we want every tenant to have this privilege against Vertex AI. So we would hit that program or that Terraform project, which is designed to run against, say, our entire tenant community, and we could tweak the part of that project that allocates privileges to a tenant, and we might say allocate this extra Vertex AI privilege for this tenant, and we would run that, and it might that project has a list of these 100 tenants, and the Terraform plan might say, I'm going to add this privilege for these 100 tenants, and you could look at that and say, yep, that's what I want to do, and you can execute on that. So that's sort of like one pattern that's used to apply Terraform in a multi-tenant strategy. Another strategy might be that like a specific tenant says, oh, I need a MySQL database just for us, just for our tenancy. So that's something where you might not want to apply it to that that one Terraform project that operates on 100 tenants. So we have another pattern that we apply, which has a Terraform project, which is just very specific to a single tenant, where we can add in things that are only relevant to that tenant. And in that way, we kind of keep that that broad tenant project free of that level of complexity. And we've sort of isolated stuff that's specific to a specific tenant, to a specific Terraform project. And it sort of like limits our blast radius for that particular project where it's only operating on that one tenant, and we can't really if we make a mistake, we're not going to affect 100 tenants. And also sort of like it gives us a spot to capture nuances that are specific to that tenant or requirements that are specific to that tenant. So that's another kind of a pattern, Terraform project pattern. Another pattern that I was alluding to earlier is one where we write the Terraform code, and this Terraform code is parameterized, and we allow the tenants to run it through CI/CD and only provide the parameters to that project. So they're not providing raw Terraform code that we have to worry about what's going on in that raw Terraform code that's provided by the development group. They're just providing parameters, and we know what the Terraform code consists of. Let's see, I think I missed this one thing about like or maybe it was on a slide, but I kind of glazed over it. But there's this, we have Terraform has a notion of TF vars files, which back to this thing about Terraform variables. So this construct where you have a variable and you're passing that variable into your Terraform code, there's this notion of a TF vars files, which is providing a set of values for every one of those variables for an entire project. And we use this pattern. It's kind of a typical pattern where we will say, for this environment, for the development environment, here are the values for all of these variables that are referenced in this code. In the test environment, here's the set of values for these variables. In the prod environment, here's the set of values for these variables. And Terraform has this like construct, they call it a TF vars file. Then it's a file that contains a set of variables, and you kind of invoke that file for the appropriate context. And that's how we use those to create environment specific set of configuration for a particular Terraform project. So, and I guess that's it. That's sort of like our whirlwind tour of how we use Terraform, how we use Terraform to support multi-tenancy in Google Cloud. And I guess I could, I don't know, I guess I could take any questions through chat or from the room.
No, I think is it the time for you?
I don't know. Oh no, that's that guy's phone. 250.
The other aspect is where HashiCorp releases some of the modules, and they tend to catch up with the actual CLA updates for the providers. So, if you have, if you need to basically run on the latest and greatest of the releases from the Google, let's say Google or Azure, then I think there's always a way to run customer servers and then refer actual CLI. So that times you won't get the Terraform construct until HashiCorp updates module. So there is a way of actually doing that. Okay?
Yeah. So
More it's on that as well.
yeah, so like there's this like Terraform has this mechanism for locking versions of its Terraform providers, and it locks them in Terraform lock HCL, because your code pretty much just said, I want to use the Google provider or the Google beta provider or the Kubernetes provider, and those all have versions associated with them. So to kind of keep you from I mean that sort of like notion is like present in things like any kind of software, bill of materials, like, like package dot, node projects, Java projects, Python projects, same thing here. Where like when you run it for the first time, it creates that log file. And if you ever want to update it, like what I do is I'll like delete that log file and then it'll grab the most recent version. Or if you really want to, you can specify versions, but I tend not to specify versions in the code itself and let that log file like dictate the versions. And if a lot of times, yeah, like there's this
I mean, especially
evolution of the versions of things. And
Yeah.
sometimes if you're running on an old version, you look at the Terraform website, it says you can use this attribute. You're like, great, let me add this attribute. You run your code and it's like, I don't know about that attribute. And then you realize because you're locked into an older version of the
Yeah.
provider.
But especially when they release newer services or service enhancements,
Mhm.
and the Terraform version doesn't catch up, and then, and you really wanted to basically do that, use that
Also,
service,
that scenario,
then basically you can use custom resource and then you run a CLI directly, right? Instead of putting a Terraform module construct. I mean, there is a way to do that.
you can, like, if you, yeah, like sometimes the most recent version, there's all those things, the most recent version available from HashiCorp
HashiCorp
doesn't
catch up,
have
yeah.
the most recent
Yeah.
version because they need a little bit of time
Yeah.
to catch up. And in that case, yeah, you could try and write your own. I mean, all those are sort of like,
I mean, HashiCorp gives that custom resource capability as well, but you have to write the whole CLI references to use that resource.
right, and that has, that's like highly undesirable, but I mean, if you get into,
that,
if you need to, it
you
kind
are
of
doing
sucks. I would,
innovation side, you want to do quick POC, yeah, that's a bit.
yeah, quick POC, like in those cases, sometimes, quick POC, we go in the lab, we create the stuff in the console and don't use Terraform at all. All right, so that's a little bit, so that's about Terraform. I didn't, let me see if there's any questions in the chat. Have you experienced Terraform? Plan pass, but failed in Terraform apply. Oh, hey, Jonathan. I can,
Hey, Tony, I'm not
Oh,
sure
hey.
you can hear me or not. Oh, you
I
are.
can hear you.
Oh, perfect. Yeah, that is we encountered sometimes in the Terraform. Let's say I do not have a IAM role defined, but when you run Terraform plan works. When you run Terraform apply failed. So not
Oh,
sure,
yes.
is there any better way to address it?
Well, there's so many variations here, like what resources you're going after, who the cloud providers are, what is actually going on. There could be strange race conditions too in Terraform code, like, so like, for instance, like, Terraform is pretty good about, creating like an ordered dependency graph of what you're asking it to do. But in some cases, you can write your Terraform code such that you kind of haven't indicated to Terraform the order and sequence of things. Like, for instance, you create an IAM, you create a service account, and then you create a bucket and you say, hey, this service account has access to this bucket. But it's possible to write that Terraform code in a way that Terraform doesn't know that there's a dependency between those things. In which case, like, you could get these race conditions where, like, plan says, hey, I'm going to do this, and you're like, hey, that's what I want to do. But when it goes to execute it, it might try to create the privilege, the IAM construct referring to the service account before the service account has been created. So that's one situation where, like, Terraform allows you to, like, if there's a depends on clause that you could use, or instead of maybe, referring to a string in a Terraform construct, you could refer to the resource itself, which lets Terraform like understand the order of things. But that's just one example where Terraform apply might fail. There's like so many different situations where it might fail that I can't really give like a one-stop shopping answer for that. And so, like, it depends on why it's failing. And there's different, strategies depending on why it's failing. And sometimes, worst case is it's like this kind of a horrible bug in the provider itself that can't be fixed. But like, usually it's not like that. A lot of times, there could be things like state problems with state, like accidentally it happens. People do things to leave state in a bad way, such that, there are ways to actually manipulate or address, manually manipulate Terraform state, which is sort of like an advanced strategy. So I can't say like, there's no like one answer to that. It really depends on why
Also can be somebody
apply
would
is
have
failing.
gone into the infrastructure manually and did some changes, and now plan will work because it is operating on a state, but apply will fail.
Well, that's another situation. And Terraform has this notion of refreshing state on the fly. Like in some cases, like when you ask it to do stuff during a plan, it actually calls out to the infrastructure and gathers up information, and it'll be pretty smart about if someone adds a label, like the plan will actually know about that. But it's not universally great about when it tries to refresh stuff for a plan. So there's like so many different,
But in those scenarios, you can run Terraform validate. It will actually do an infrastructure call, and it will basically try to tell you, you're just in a louder place, you are adrift in your actual infrastructure. One way to do it,
Yeah, sometimes plan isn't good enough and it doesn't do, because like that depends on the way that the provider's been written, how it responds to validate or refresh. Sometimes your plan says, I'm going to create this IAM thing. But actually someone had added the IAM thing. And when it goes to apply it, it's like that IAM thing already exists. And then you're like, damn. And so you can either like import the IAM thing into your state or manually delete it, and it depends what it is. So let's see, what should I do? I'm like, I didn't touch on GKE.
Just a little bit further on, that scenario runs on provisioning for GCP resources, and it was a typo and it was being introduced, but Terraform plan does not catch that. And my understanding is that Terraform is not only just to do syntax checking, but also really looking into each elements. Should prevent that happen, I will say the plan should catch that, but it's not, and it ends to be when you apply, when you do Terraform apply, then failed. That's the whole story.
Yeah,
So,
I mean, I would say like, again, it would have to be like the conversation would be, it might, there are situations where, yeah, there's legitimate enhancement requests to the Terraform providers, and that's why, if you go on Terraform, the Terraform GitHub, you'll see there's, plenty of issues there too.
cool, thanks.
I think, Jonathan, the process for Terraform to verify is to check the Terraform state. So if there's any manual setup, the Terraform state won't be able to catch that.
Yeah.
So that's
So
the major thing we run into before.
So there's another way, right? You provision infrastructure, and now you do a reverse engineering to create the state, right? So for example, the scenario what he told, right? So I created everything in local, the state file is in local. Now, somebody created a state file, an infrastructure provision. How do you just take that back? So you need to create the state back. So one way to basically do is, okay, from the infrastructure, you create the state, and then, you really run after that. So, it's a different problem actually. You have to export, and then you have to really apply in those things. I think in his cases, maybe I think he has a drift, definitely.
I know,
Or is that
there's so
release
many,
version
there's so many different
many
variations.
Yeah.
Anyway, so, let's see, so should I do?
Situation like while running a CI/CD, your TFS state file got logged, and you have the
Oh,
option.
The
Only option I have to delete that state file.
Or it's the Windows restart.
How do you deal with
After
that?
some time it will work.
Yeah.
I have failed in production, and it was a nightmare for me, working for 14 hours, my state file logged, and I was not able to convince my admin team, like, it's not my issue. I am running for the first time. And finally, they like agreed on me, they deleted the state file, and then it went fine.
In fact, I think Tony and I, we face this really weird thing with Terraform, and especially working on AWS IAM and applying some new permissions. The plan didn't catch it, but the did go ahead and went on with this new patch of our IAM permissions and logged us out completely.
Mm,
We have to go in with a different service account.
The plan does not-
Yeah, that isn't fair.
Keep state file.
yeah, so sometimes, yeah, and typically you don't want like end users to manually manipulate state to be able to remove lock files. So like that would be like a call to someone with root privileges to delete that lock file in the state bucket. And that could be a
In
hassle.
that case, right, I think your state is not refreshed with the actual IAM properties. Now, you're flipping the service account, now it changed because it's actually fetching from there and create the state. That's a new resource, it's new, right? That's the reason.
It will be new also.
That's the reason we got it.
And Tony, the wrapper script that you're talking about, so does it take care of deleting the infrastructure as well? Because sometimes when we are trying to delete, say like a custom image, it also tries to delete all the clusters that were created is the custom image, right?
Well, I would say it's not the wrapper that deletes state. Terraform itself is like declarative. So you kind of say, I want the infrastructure to look like this. And if you've removed a bucket from your Terraform project, Terraform plan will say, I'm going to delete this bucket.
And all its dependencies. right?
And well,
Like
if-
say, Dataflow is
if
in the
your
custom-
project is written in a way such that it knows about the dependencies, yeah. So Terraform does that itself. It's not the wrapper script.
Is there a way to like control the deletion of infrastructure like in the Terraform? Currently, when we run Terraform, run and apply or auto apply, it automatically applies, right? So how are we doing in custom prod with Jenkins? Like, is there any manual person reviewing the plan output and apply?
Yeah, we have like our Jenkins like has this dry run. So which is like plan for like dry run is like a generic abstract term, but when it's applied to a Terraform project, it means Terraform plan. And so we have people like look at the output of Terraform plan. And some of our stuff is can get pretty like involved to the point where like Terraform plan could be pretty nasty, but usually, so either we know about it, like we're applying, say, one privilege to 100 tenants and we expect it, and you kind of like look at it and you're like, yeah. And then sometimes you're expecting, hey, I'm doing something really, really simple, and it comes back and says, I'm gonna do all this stuff. And then you're like, that doesn't sound right to me. And so then we have to kind of troubleshoot that. So can anyone care if I go through the GKE presentation?
Sure.
I know I'm sort of like I'm off the time schedule, but
No, yeah.
Sure.
okay. All right, so the next session is about Kubernetes and how it sort of maps to multi-tenancy. The agenda a little bit, I'll talk a little bit about Terraform since we just talked about Terraform, but how Terraform applies to Kubernetes. Kubernetes namespaces, how we use those, how CI/CD plays into it. Helm charts, or a specific Helm chart that we use, a particular Helm chart. Persistent volume, secrets, and workload identity federation, which is a GCP specific thing, which is pretty cool. And then we'll summarize. So let's go. So a little bit about Kubernetes is awesome. Big fan of Kubernetes. I think everyone mostly is familiar with it, but it's sort of like a virtual, it's like a virtual machine of virtual machines, or a virtual data center in a way, where under the hood, it's supported by a whole bunch of virtual machines and some scheduling logic to vastly oversimplify it. But it has all these great features, which we love, which we used to, back in the old days, we needed to do it all manually, and it took a lot of effort and manpower and automation, and it's all built into Kubernetes. Things like bin packing, which is basically like making when you have a piece of hardware, making sure that before you allocate and pay for another piece of hardware, that you've used up this first piece of hardware effectively and efficiently. Or self-healing. So if you have like, if you've ever done this the old way, you provisioned 5 VMs, let's say, to run this application on it. And if one of those VMs like chokes for some reason, like you kind of want to know about it. So in the old days, you would have to write some kind of automation. Either you know about it the bad way, which is your customer calls you up and says, our system isn't working well, and then you have to go troubleshoot it, or you know about it the good way, but you had to write a whole bunch of automation to support it. You know, like maybe you're asking that virtual machine, you're pinging it or something, and you're saying, are you up? Are you up? Are you up? Are you there? Or a process on that machine, like, hey, is this process up? Is this process up? Is this process up? Is this process isn't up? Spin up the process, and you've written all that stuff, and it's a lot of effort to write all that in a customized way. But you get, this is kind of like what Kubernetes does. It also is good about scaling and advanced features like automatically scaling. So like in the old days, you'd say, you know, let me create 2 machines and 2 instances of this process on each machine. And then if it wasn't keeping up with the volumes, you'd have to figure that out, and you'd have to say, well, maybe let me add a 3rd machine and add 2 more instances of this process, or another instance of this process on this other machine, or another thread in this process, or whatever. And Kubernetes' reason for being, or, you know, one of the things it does is this automated scaling, where you can just say, hey, you're running some workload for me at this scaling level. And you can even sort of like get fancy, which is gathering metrics on your workload real time, like, hey, is the CPU in this particular process, did it go past a certain threshold? Did the memory in this particular process go past a certain threshold? Are these SLAs, SLOs that I've set for this, like, is it responding in less than 100 milliseconds per call? Things like that. You can feed all that back into automatically scaling it up to, say, either add machines or add pods. So it's pretty sophisticated, and there's a lot of sort of tooling built around it to help you do just that, which is to automate the scaling based on live metrics. So that's a little of the awesomeness of Kubernetes. GKE is GCP's managed Kubernetes. All the cloud providers have managed Kubernetes. AWS has EKS, which is their managed Kubernetes. Azure has AKS, which is their Kubernetes. Kubernetes is good. Terraform. So how Terraform comes into play in the Kubernetes discussion is that there's a Kubernetes provider for Terraform. So that allows us to do things like create Kubernetes constructs with Terraform code that we're, you know, familiar with, and we get that cool declarative aspect of it. So instead of like, you know, maybe a more cumbersome way to create stuff, and then if you want to delete it, like later on, you write some code that says delete this. So you write some code that says create this, and then later on you're like, oh, I don't need that anymore. You write some other code to delete it. Instead of that, in Terraform, you can just say, I want this to look like this. So initially you could say, I want this to have 3 VMs. And then you roll it out. And then later you can say, no, I just want 2 VMs. And so Terraform is smart enough to do the math and say, all right, that means I need to delete this VM. So you get all that goodness with Kubernetes constructs like namespaces, or like Kubernetes has a notion of service accounts, or Kubernetes has a notion of roles and privileges applied to service accounts, like these policies. And I think that's, yeah, like mostly what we use. That's sort of how we use Terraform to create Kubernetes constructs, and they're applied to And I'll talk a little bit more about how they map to our notion of a tenant. So namespaces are, we use namespaces to create a boundary around the tenant. And so namespaces are construct in Kubernetes, which is basically just a boundary or a collection of things running in Kubernetes. And so like we might have a tenant called XYZ, we'll create a namespace called XYZ in our Kubernetes cluster. With respect to multi-tenancy, there's a lot of ways to do this, but we have, say, a dev Kubernetes cluster for all of our tenants in the dev environment, and we'll create namespaces for them in the dev Kubernetes cluster. We also have a test Kubernetes cluster, and we'll create the namespaces for them in test. Same thing with prod. Some people, there's all sorts of different variations on that. Some people will co-locate test and dev in the same cluster. They'll call it a non-prod cluster. They'll have like XYZ dev namespace, XYZ test namespace. There's different ways to do that. And then when that tenant wants to deploy workloads out for their tenancy, we deploy those workloads out into that namespace. So everything all of that tenant's workload is in that namespace. And it allows us to kind of create like privileging around that too. So we can give that tenant credentials that gives them a certain amount of power within that namespace that's localized to the constructs that are running in that namespace. Like, so for instance, the ability to scale a pod from 2 to 3 or from 3 to 0 or anything like that. We can create Kubernetes has this like policy system where that allows you to specify something like that. Like here's this privilege that allows you to scale a pod in this namespace. What else?
You're basically saying that a namespace cannot be nested inside another namespace. Is that the point of the?
Well, that's one bullet up there. And you can't nest namespaces. That's just kind of the way it works. And it's probably a good thing because we have enough things to worry about without nested namespaces. I don't know that it would add a ton of value here. So it's not, I haven't found that as a loss, or I have never found myself wishing I could nest namespaces. And just generally speaking, like when we our automated deployment, our CI/CD system knows the tenancy of the particular, we use Jenkins, the Jenkins job knows the tenancy of the job that it's working through. So when it goes to deploy something to Kubernetes, it knows what namespace to deploy it to. So it constructs some Kubernetes YAML. Kubernetes is, everything, all its configuration is YAML based. Jenkins constructs some YAML that specifies for Kubernetes to deploy that workload to the appropriate namespace. So that's it for namespaces. CI/CD, I was kind of touching on it earlier. So let's see. So we run Jenkins, our CI/CD system, on Kubernetes itself. There's this cool plugin. Jenkins itself is like has this plugin strategy, and there's tons of like plugins for Jenkins. And we use this plugin that allows Jenkins to spin up Jenkins jobs dynamically in Kubernetes. And then when they're done, they kind of go away. So it's pretty cool the way that it can do that. And it uses the Kubernetes infrastructure to sort of scale up and down Jenkins CI/CD workloads. In the old days, like I've been working with Jenkins for many, many years. In the old days, we to scale Jenkins, we needed to create it'd be pretty like a typical setup would be to provision a a bare metal machine for Jenkins, or, you know, or in VMware, provision of VM for Jenkins, provision VMs for Jenkins slaves, they call them. And the different slaves would need the stack elements that the Jenkins job needed to run. So for instance, if you were running some kind of Jenkins job that needed NPM or Node to run some node-based tests, that Jenkins slave would have to have Node installed on it, and maybe even specific versions of Node on it. And you can kind of in your mind, like, imagine the resource intensive nature of that, where people are like, I need Java 8, I need Java 11, I need Node 10, I need, you know, Python 20, or, you know, Python 3, 3.6. Like, really, I mean, Jenkins is great, but that part of it was pretty cumbersome, and it would take, you know, usually only certain groups provisioned those slaves and configured them, and it was pretty like involved and cumbersome. So what with this Jenkins Kubernetes plugin, it allows you to sort of use the expandability, the elasticity, the elastic compute nature of, well, the cloud and Kubernetes itself. It also allows you to define these jobs in Jenkins that refer to containers. So instead of like installing Node on a slave machine in your Jenkins flow, you could say something like, within the context of a container within the context of this container image, execute these command lines. And that container image can be dynamic. So to the point, so where you could actually parameterize this thing with the version of Node you want to run. And what Jenkins does at runtime is it reaches out to say something like a Docker hub and says, give me this version of Node, and it grabs a container, and it grabs the container containing the version of Node that you want to run on, and then it executes your NPM test in the context of that. So like, it's really like pretty innovative, especially if you've done it the old way and have that experience with the old way first. So that's something we use to run to provision Jenkins workloads on Kubernetes itself, allow those workloads to use arbitrary containers to be able to use, you know, like an arbitrary set of stack elements in Jenkins workflows. We use this Jenkins shared library construct to house like this reusable flows that we engineered that are generic flows that could do something like build a Spring Boot application based on a Maven POM file, turn it into a Docker container, push that Docker container to a container registry, construct the YAML required to request that Kubernetes run that container containing the Spring Boot application on Kubernetes with, say, a certain number of pods or some kind of like Kubernetes like specification. So that's how we use the Jenkins shared library construct. We use this thing called GitHub branch source plugin, which is another great plugin that you can attach to a GitHub organization. And for every GitHub organization repository branch triple, there's this automation handshake between GitHub and Jenkins that automatically creates a job that represents, that sort of gloms onto that GitHub organization repo branch triple, and it creates jobs automatically, and it can even start them automatically. And so that's another construct that we use to help automate this, to, you know, create a self-service construct for our tenants, such that as like, there's sort of some initial setup to associate a GitHub organization with Jenkins. We use a webhook on the GitHub organization at the GitHub organization level, such that anytime stuff happens in GitHub, it tells Jenkins about it. It feeds into this plugin. That plugin will create Jenkins jobs that correspond to that. So we get a lot of great self-service automation from that, so that all a tenant has to do is create a repo and a branch in that organization with kind of, there's like this signature that Jenkins looks for to create a job. And it could be something like a Jenkins file, which is like this little snippet of Groovy code that sort of like tells Jenkins that, yes, this is a repository branch that should have a job automatically created for it. What else? The role-based up. So we use like some like basically like it's a security related authorization plugin that allows us to say, like, for a particular tenant, if when a human logs into the Jenkins UI, we can either allow or disallow that human access to certain folders and jobs in Jenkins based on their Active Directory membership. So that's how we sort of kind of control visibility and abilities for different tenants to see stuff that only they should see within Jenkins. What else? We use a Helm. We use a Helm chart. Helm, for anyone that's not familiar, Helm is like a packaging construct for Kubernetes. So it defines the ability to deploy things on Kubernetes. Think about it as just a bunch of Kubernetes YAML that can be parameterized. And there's a Helm chart available for Jenkins that we use to configure Jenkins when we deploy it out to Kubernetes. And there's this other configuration as code plugin that allows you to define the configuration of Jenkins in YAML, which is, it might be, again, it's like maybe not that impressive on the face of it, but if you knew how Jenkins was configured like 5 years ago, you'd be more appreciative of it. It was not as smooth as through with the benefit of this plugin here. And so when we add a tenant, we also add a little bit of configuration in Jenkins that kind of configures this authorization plugin to allow them to see and maybe kick off jobs in Jenkins based on their membership in these Active Directory projects. So like when we onboard a new tenant, we tweak some of this Jenkins configuration and we redeploy that configuration out so that the appropriate sort of like authorization for that tenant is built into Jenkins. What else? Microservice Helm chart. So I just talked a little about Helm. Helm is like a set of YAML configuration for Kubernetes that you can parameterize. We found that, like, say for Kubernetes microservices deployed to Kubernetes, whether they're Java-based, Node-based, Python-based, that they all sort of like follow this same similar pattern. So we created a Helm chart that captures that pattern, and it's just slightly parameterized. When Jenkins deploys stuff out to Kubernetes, it might just provide stuff like the namespace as a parameter, like, the tenant name, tenant XYZ goes to this namespace. And we allow for the tenant to provide some configuration in their repository that Jenkins grabs and integrates into this Helm chart to kind of create the configuration that Kubernetes uses to run that tenant's microservice. So yeah, for example, things like maybe you want to reference a persistent volume, maybe you want to add a sidecar, maybe you want to say, hey, only run on this node pool. Or maybe you want to say, hey, I'm gonna need 3 CPUs or 3 meg of memory for this, or 3 gig of memory for this workload. So that's how we use this microservice Helm chart. This is something we came up with, but that's super useful. So that sort of like means that our tenants that want to deploy microservices, they don't really have to get involved with that level of detail. We just sort of like, even under the hood, Jenkins just does this stuff for them through this reusable flow. And it's just sort of like, it simplifies. So like general philosophy here is to like sensible defaults such that, like it should be pretty easy to do something pretty standardized. But sometimes like, different workloads have very specific needs. So allow configuration hooks when the sort of the default is not sufficient. Persistent volumes in Kubernetes. So yeah, we use some of the, like we run certain things in Kubernetes ourselves, certain sort of like infrastructure components like Jenkins, like Nexus, like Vault. We run all of those in Kubernetes, which is great. All those happen to use persistent volumes because they just, the way they're implemented, they sort of depend on file systems. But we also have the ability to construct persistent volumes, which are file systems that workloads on Kubernetes can see. And you might think like, if you instinctively, you might be like, what's the big deal? But if you think about the way Kubernetes operates, your workloads are running on different machines. And so like, in order for them to be able to die on one machine and come up on another machine, or scale out across many, many machines and still have access to the same file system, it's basically like an NFS construct. And so there's this, Kubernetes has this abstraction of persistent volumes, and then there's these implementations of those persistent volumes. They're like kind of pluggable implementations. One of them is Google File Store, which is Google's managed NFS, and we use that to back persistent volumes. And we have a strategy where we can set up a persistent volume for a tenant and make it accessible to their workloads that they run on GKE. Not everyone uses, it's kind of like, it's not that common, but sometimes people need file systems for some reason. A lot of times, like, having state on a file system is like not always the best. So a lot of times we use like databases are a much more elegant way to share state amongst workloads running in Kubernetes. Secrets, another thing, we use HashiCorp Vault. So another cool HashiCorp product, Terraform and Vault. We use their open source version of it. And we use another open source component from Bonsai Cloud. They created this mechanism which integrates Vault and workloads running in Kubernetes. So what it does is it can grab secrets from Vault and present them to workloads running on Kubernetes as environment variables. And we do that in kind of this like safe way that also aligns with tenancy constructs, such that tenants are only allowed to read their own secrets. Tenant workloads are aligned with their own secrets, and tenants can't read other secrets. So Bonsai Cloud, this guy is helpful for that. Workload identity federation is this kind of really cool construct that GCP has provided within GKE, which allows GKE workloads to assume the identity of a particular principal, giving them access to resources that only that principal should have access to. And we use this in a way that aligns with our tenant construct, such that things running in a particular tenant's workspace, they automatically run as a particular service account principal for that tenant, and they gain access to that tenant's resources. So that's it. Thanks for listening. I know I went over.
One question.
Oh, chat? Do you run Jenkins on Kate's in GCP or in on-prem environment? Jonathan, you there? Oh, that was like 20 minutes ago. No, that was 10 minutes ago. He might have left, but,
It's fine, you can publish him, after you go.
yeah.
No worries. No.
So, yeah, just, we don't run it. Well, yeah, actually, Adner does run Jenkins on-prem, but
Yeah.
our group runs it, in in
No,
Kubernetes.
yeah, Just GCP, right?
So that's it. Thanks for listening. Sorry I went over. Bingway came in, shut us down.
Like, thank God, then they came. in.
I started late, though. In my
Right.
defense.
Yeah.
It is
That's
like-
all right, yeah. So, I guess, are you doing I joined the meeting, yeah. Is it already recording now?
You can use
It is
the
recording,
data.
right?
Yes.
Okay.
You can see here.
Oh, do they have drinks?
Not booze.